All right, and I'm pleased to introduce Dr. Susan Kassin from Space Telescope. She'll be presenting the work of her group using a really innovative technique with James Webb NIRSpec.
Thank you, Jen. Very kind of you. So I will be talking about hold your breath. I'm going to take the lights out because, and I'm going to put them back on to wake you out because we got pictures. I'm an observer. I think that'll work. I hit it once. Oh, there it goes. So I want to mention this is work. I'm presenting this on behalf of our team, Camilla Pacifici, Celia Mulcahy, Ezra Suke. Ezra, you saw his poster. Celia will be talking soon. Jane Morrison, Eddie Bergeron, Mike Reagan. Eddie's present. Everyone in green is present. We're amongst family and friends here. So we chose 2 galaxies to study for this talk. And we chose them from Hubble images because they were these beautiful mergers. We thought, oh, let's just study these. Let's get kinematics of them. Let's get spectra and study them. Okay, but I'm going to walk you through kinematics. So I'm going to give you a baseline of what we see at redshift 0, courtesy Ben Wiener. This is Fabry-Perot or kinematics observations of a local galaxy at redshift 0. And the top row, on the bottom row, is it's redshifted to redshift 1 with seeing. So as observed, smooth with seeing. This is an image. This is it blurred. Simple. Velocity map, it's spinning. Blue is going toward us. Red is going away. It's spinning. Here it is blurred. Not so hard. Here's velocity dispersion. But when you blur it, you get a peak in the center. This is only due to the rise in the rotation curve. So you see a delta V in the rotation curve that becomes a velocity dispersion. I believe Ben was the first to point this out. And it's how people actually identify disks at high redshift now. State-of-the-art from ground base is done with adaptive optics. These are beautiful observations by Natasha Forster-Schreiber and her team. They kind of show this velocity dispersion. Velocity dispersion is sometimes a peak in the center, but it's often high peaks throughout. It's just kind of convoluted mess. So it's kind of tough going and kind of interpreting these maps, in my personal opinion. And that's where we came in with James Webb. We created the garden survey because Sandy taught us you should name things. And we used something called the microshutter on James Webb. And I'm going to show you what that is because we think it's just so cool. The microshutter array allows you to take spectra of galaxies by opening little shutters, and it allows you to take over a large field of view, like a multi-object spectrograph on the ground. 3.5 arc minutes on a side. Here it is in the lab. There are 4 quadrants with these little shutters that you can address and open and close. There it is on the sky. 3.5 arc minutes on the side. That's a number to remember. You can get hundreds or thousands of spectra at the same time. Here's a deep field image. We're going to zoom into that little box over there. You see the user here is open these little orange and red shutters over the galaxies, zooming in here over their little special spots. You don't get the whole spectra throughout the whole galaxy. You get it wherever you put that slit. In an IFU, which is small on Webb, it's 3.5 arc seconds on a side. So 3.5 arc minutes for the MOS, 3.5 arc seconds for the IFU. But with the IFU, it's beautiful. You get a spectrum in each pixel. You can create these maps in one shot for a galaxy. So what we did, it's been done from the ground for years. We just simply moved the telescope pointing across the galaxy. We call it slitlet stepping because one of these long things for the MSA is called a slitlet. I'm moving quick through the observational parts to get to the science so you can get out of here. So what we did for this is a schematic of one of those MSA quadrants. You could fit a lot more galaxies. This is not to scale. But for some of the galaxies that are large, we do 6 steps. Smaller ones, we do 5, 4, 3, 2. And you get down to ones that fit in a shutter, 1. So what we're doing is shifting the MSA. And for this, we do nothing. For these, we shift and we reconfigure. We close this shutter and we open the one behind it, close it and open the one behind it. And you can fit that many more galaxies in. And then for the observers, we do a dither pattern through it to cover the gaps. I'm not going to go into too much detail on the details of the observations. We did this for 56 galaxies. We used the R of 3000, the higher resolution, the less galaxies you can fit. We went very deep. So we spent the last year and a half or so really working on the reductions, and you're welcome to talk with us about that. So 60 hours on source, 10 hours per step. All data were publicly available immediately, and we're hoping to reduce cubes soon. If you did this with the IFU, it would take you like 4 months. So we thought it was worth it to try to see if it would work. These are the galaxies in the sample. This is in the UDF. We chose beautiful things, bright things, Steidel-like objects, because this was a cycle 1 program, unfortunately observed in cycle 2, but we didn't know what would happen with the telescope. We were hoping it would launch. Okay, now we're going to slow down. I'm going to walk you through beautiful pictures of these merging galaxies led by Ezra Souquet and Celia Mulcahy, both graduate students at Johns Hopkins. I have a pleasure of working with. First, we give them names, because if not, who wants to memorize all those call numbers? This one looks like the coffee pot. Why not, guys? Now this is the Webb image. Isn't that amazing? I'm going to do it again. Hubble, Webb. Look at that dust enshrouded center, all those clumpy clusters, the dust on the inner part of that spiral arm. And thank you, Brant, if you're in the room, for making those JWST images with your team. Here it is in different wave bands. We're breaking it down, UV, B, J band. You start seeing the semblance of a bar and arms, perhaps. For those of you who really want to take a liberties, bar, arms. Here's the state of the art from ground base. This is what we were doing before Webb launched. Now I'm going to show you the Webb stuff. That's the $10 billion difference, people. We went from kind of blurry things to really putting glasses on. Now I'm going to walk you through the beautiful maps. First, we're going to start with H alpha. When I first saw this, it shocked me because I'm like, oh, we're studying a merger. Why does it look like, I think I see spiral like arms in a bar. Maybe, maybe not. I'm not sold on it. It has an overall sense of rotation. It goes from, if you're the reds going away from you, the blues going towards you. It's an overall sense of rotation in this object. Reasonable amount. But overall, there's a lot of details in this map. You see this spot here is going away from us. That one, that's that deep red. You see a lot of modeledness. This zero velocity line has a lot of wiggles. There's a lot of complexity to the system. And I should say that this velocity map is not affected by the clumps. There's these giant star-forming clumps. Velocity map doesn't seem to care too much. Now, this is a velocity dispersion map. This is my favorite. When Ezra first showed this to me, I didn't believe it fully. In the inner part of, so you notice it has this very high velocity dispersion in here, in the inner part of the arms. And then what happens is, I can't walk over there because I'm going to have feedback, but there's another arm here and here on both sides. They wrap around. It's incredible. I think our spectroscopy go deeper than the images. The other thing is the clumps. Look at where they are. They're in the, thank you, it's much better. Thank you. They're in the black regions. Black regions are low velocity dispersion. They're forming where they should be, in regions of low turmeric hue. And Ezra's poster outside, please go see it. He has evidence for this inner arm kind of swirl thing being shocks. Oh, this is thank you, a laser pointer. Took me a minute. It's just showing the contours that show that the velocity dispersion happens in the inner arm region and in the center over here, where there's probably a weak AGN, in my opinion. And keep in mind, this velocity dispersion goes up to 180 kilometers per second. It's no joke. We call it As we're naming things now, we call this the cinnamon bun structure, swirl structure. And we don't seem to see this at Redshift 0. We've looked, given it this talk at conferences, people don't see this at Redshift 0, as far as I can tell. If you do know of it, please let me know. Now we're going to walk you through the bear claw. Celia is going to talk about this in a lot more detail, but I'd like you to see it twice. We call it the bear claw. If you've ever been to Panera Bread, you can order it. It's a pastry. Again, zooming into that web image, we fought to get this observed on our mask, and Celia and I had a cow when we saw it was when you look at the Jade's image, it looks like a disc with a very dust enshrouded center. Look how red that is. You don't even see it here. Ooh, spooky. These giant clumps. Oh, you should see. Look, okay, so first look at the clumps. Some of them break up in here. Some of them stay. Mix of both. So she made these beautiful F90 images that show the clumps, and then the dress J bands, which shows a bar, and perhaps spiral arms. You know, these mergers are growing arms and bars and stuff. It's remarkable. So this is F90. And next to it is a velocity map. It has that beautiful Pepsi sign. You see, that's the zero velocity line for the experts. This is an odd feature here, but it is perpendicular to the bar. Oh, there's the contours. It does exactly what it would do in the local universe. Beautiful velocity gradient, zero velocity line, weird turn down over here, but you know, rotates pretty damn fast. Nice rotating disk with a little bit of weirdness. Velocity dispersion. Again, the clumps are in the, it goes up to 120, cinnamon bun swirl structure. Again, inside that inner arm. See, it fits right in there. And then there's another arm out here. We went really deep. We're like, wow. And that's thanks to the hard work by Eddie Bergeron here and Mike Reagan, who helped us with those special reductions. The clumps tend to form like in these black regions. This is a little different. This one's a little odd, but these tend to form in the black regions. And that's the J band, showing the bar and the arms. So keeping it short and sweet, slit stepping works. With these kinematic maps at Redshift 2, they show galaxies are not just a bunch of active clumps blowing things out. They reveal unexplained high gas velocity dispersions in the inner arm regions. The clumps form in regions of low sigma. Disk or merger. I think it's really too simple a dichotomy at Redshift 2, where the gas fractions are high and the mergers are expected to create disks. Last slide. You know, we love this scenario that where Phil Hopkins put this wonderful, I bastardized his figure, but his wonderful figure together showing how you have mergers form lurgs and then form an early type. Perhaps at Redshift 2, you have mergers that form, you have galaxies that merge and then form kind of, you have these gaseous mergers that then form a disk. So you have this kind of Franken disk merger objects. Thank you.
Thanks, Susan. All right, got time for maybe one or two questions. And if Lou could come up and get plugged in, that'd be great. Lisa?
Susan, this is beautiful data. I'm wondering whether you've looked at the clumps over here.
The what?
I'm wondering if you've looked at the clump sizes and whether they follow any sort of scaling relations or the you know, mass functions that they've found in like the dynamo sample or that Emily Wisniewski found quite a while back now at ZIV2.
We haven't yet. Thank you, though. It's a good point.
Okay, one more question.
I guess hi. I'll keep it quick. I was curious if there is other complementary data for these objects in terms of MIRI, like tracing the pause, or ALMA with the dust in term. It reminded me a lot of like the Jackie Hodge, sort of all these different components. I think it's from our like 2015 paper where you're seeing all these different components at different wavelengths.
I could show you, yes, for the coffee pot. It's one of David Elbaz's like starbursty, dusty starbursty things, and the ALMA is right over the dust there, as is the MIRI. The MIRI shows beautiful stuff. Yeah.
Okay, let's thank Susan again.